In today's lesson, we're going to be looking at powers again. So we talked a little bit before about powers and basically what they represent. Now we're going to be looking at doing some calculations with powers and exponents. So when we use powers and expressions to represent quantities and solve problems, we often need to carry out operations with those powers. Right? So it's not just as simple as just understanding what they represent in terms of a number or the base multiplied by itself multiple times. We also need to carry out operations that involve multiple powers. One thing to note are coefficients. Right? So coefficients are a number or maybe a letter that is in front of the power. And the coefficient is not part of the power. So if we look at the two examples here, we have 5 times 2 to the power of 6. This 5 here is our coefficient. And we can see that when we expand it, that 5 is not included in the power. Only the 2 is, because that exponent is only attached to the brackets, which includes that 2 and not the 5. We can see in the other example with the 3 is our coefficient. Right? We have 3n to the power of 5. The 5 is only attached to the n. So it's 3 and then 5 n's, or 3 multiplied and then 5 n's after. If we wanted that 3 included in the power, we would have to put brackets around the entire thing. And then in that case, then it would be 3n times 3n and so on. So only if it's included in brackets, or so only if it's included in brackets will you have multiple things attached to that exponent. When expanding, the coefficient only occurs once, right? So we see here the coefficient only occurs once, while the base is multiplied many times, as we normally do with powers. So we're going to look first at what happens when we multiply powers together. So here we want to consider the product of the powers 4 to the power of 3 times 4 to the power of 5. And we're going to write this expression in expanded form. So basically we're going to write what these two powers represent. 4 to the power of 3 means 4 times 4 times 4. And all of that is multiplied by 4 to the power of 5, which is basically 5 fours, all multiplied together. So this is what we call the expanded form, because basically it's just the expanded version or the larger version of our powers. How many factors of 4 occur in the product? Well, if we look at it, we see 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 fours all multiplied together. So that means, we have 8 fours. So that means as our answer as a product or as a single power would be 4 to the power of 8. And what we want to think about is how does this exponent, or how does the exponent of this product relate to my two original exponents up here? So how do these two represent or relate to that 8? And what we should find is that they add to 8, or they add to the power of the product, right? Or basically my new exponent. The old exponents add to that. So that's our rule when we multiply powers. When we multiply powers, say for example we have b to the power of x times b to the power of y. When we have the same base, the answer is b to the power of x plus y, or my two exponents added together. So I'm going to go through a couple of each one, and I'll let you try the last two on your own. So for example, in 1a, we have 2 to the power of 3 times 2 to the power of 5. This becomes 2 to the power of 3 plus 5, because they have the same base, so we add our exponents. So here we have 2 to the power of 8. b we have 3 to the power of 2 times 3 to the power of 3, the same base. So we can use our rule, which would be 3 to the power of 2 plus 3, which is 3 to the power of 5. I'll leave C for you to try on your own. For 2a, here we have two letters, n to the power of 3 times n to the power of 7. So even though we have letters, the same rule applies. The same base of n, 3 plus 7, will be our exponent, n to the power of 8. For b, x to the power of 4 times x to the power of, well, I don't see anything here. But we can assume that if we don't see an exponent, that it's 1. So no exponent visible equals 1. So if we don't see an exponent, we assume that it's 1. So this would be x to the power of 4 plus 1, which becomes x to the power of 5. I'm just going to give you a quick second to try the last two, both C's, on your own, and we'll check back in a quick second. So in our last two, 10 to the power of 6 times 10 to the power of 1, you should have gotten 10 to the power of 7. And for C, for number 2, even though we have 3 powers multiplied, we're still going to add them all because we have the same base of p. So p to the power of 4 plus 4 plus 2, which gives me p to the power of 10. We're going to move on from multiplying powers to dividing powers. So consider the following quotient, or basically division, of powers. 3 to the power of 6 divided by 3 to the power of 4. If we were to write this in expanded form, similar to what we did before, we would have 6 3's on top and 4 3's on the bottom. We want to think about how can this fraction be simplified. Well, if I look at this fraction, I'm just going to rewrite it quickly. So 6 3's on top, 6 3's on bottom, or sorry, 4 3's on the bottom. When I'm multiplying numbers and dividing numbers, if I'm dividing by the same number, I can cancel it out. So for example, 3 divided by 3 would cancel out. It would just give me 1, or basically they cancel out. Another 3 and another 3 would cancel out. A third 3 and a fourth 3 would cancel each other out. This would leave me with 3 times 3, or 9. How can I write this answer that I just got as a power? Well, 3 times 3, that means the base is 3. It's multiplied by itself twice, which means we have an exponent of 2. So how does this exponent here relate to these two original exponents up here? Well, if you take a look at them, the exponents are subtracted. So that's the rule when we're dividing exponents, which does kind of make sense because that's the opposite of multiplying, right? The opposite of multiplying is dividing. So that means the opposite of the one rule where we're adding, we're going to be subtracting. So if I have b to the power of x divided by b to the power of y, I would then have, or if in a simplified form, b to the power of x minus y. And there is a special case when we're dealing with this quotient rule, which kind of gives us another rule. So if I use the quotient of the powers rule to simplify the following: 5 to the power of 7 divided by 5 to the power of 7, well, I get 5 to the power of 7 minus 7, which equals 5 to the power of 0. And what should this expression equal? Now, your first instinct might be to say 5, but if you plugged in 5 to the power of 0, you would get something else. Additionally, if you looked at our fraction, I have the same number on top and the same number on the bottom. So those two would cancel each other out and leave me with, I still need a placeholder, they would leave me with 1. Or basically I have a whole fraction. So the rule, when I have b to the power of 0, or basically any base to the power of 0, it's always going to equal 1. I just have to be careful though that I'm not using a situation where I have 0 to the power of anything. So as long as b is any number but 0, when it's to the exponent of 0, it equals 1. So let's simplify the following expressions. I'll do the first couple and leave you with a few to try on your own. So for a, again, I'm going to subtract the exponents because it's division. So 12 minus 8 gives me 2 to the power of 4. For b, 3 to the power of 10 divided by 3 to the power of 9 gives me 3 to the power of 10 minus 9, which is 3 to the power of 1, or just 3. I'll leave C for you to do on your own. And for D, when I have multiple operations here, we do kind of have to refer back to our BEDMAS, if we remember that, which means I have to kind of do any brackets or then division, multiplication, so on, basically give me an order to the operations. Here, when I have a fraction like this, I can assume that on the top there's brackets around that. So I have to simplify the top first before I can divide. So I have to do my multiplying power rules here. So 4 to the power of 6 times 4 to the power of 4 means 4 to the power of 6 plus 4. Still divided by 4 to the power of 10. This gives me 4 to the power of 10 divided by 4 to the power of 10. Now that we're dividing powers, let me just bring this back up here. I'm going to subtract my exponents, which gives me 4 to the power of 0, which we've just said before equals 1. For 2a, so even though I'm using letters, the same rule applies. T to the power of 12 minus 5, get t to the power of 7. For b, q to the power of 15 divided by q, or q to the power of 1, means 15 minus 1. I get q to the power of 14. So I'll leave c in both examples or both numbers for you to try on your own. So coming back and looking at C for both of my answers, I should have 5 to the power of 2, and I should have n to the power of 4. So those should be my two answers there, again, using the rules that we've kind of already discussed. Our last rule that we're going to look at is when we have a power of a power. So this is basically when I have two powers in the same kind of expression. So what happens if the base of a power is a power itself? So like we see here. So I'm going to rewrite this or the following expression in expanded form. So if I look at this, x to the power of 3 to the power of 4, that means I have 4 groups of x to the power of 3. If I want to continue to expand this, I know that x to the power of 3 means x times x times x, and I need to repeat that 4 times. So another group of 3x's, a third group of 3x's, and finally a fourth group of 3x's. So how many factors of x do I have in this expansion or this expanded form? So if you go through and count all of them, you should find that you have 12 x's all multiplied together. So if I have x times x times x times x and so on, I can simplify that by saying x to the power of 12. Now I want to think about, and again, how does this exponent relate to these two exponents? Well, if I take a look at them, how do 4 and 3 relate to 12? Well, the exponents multiply together. So 3 times 4 gives me 12. So the rule, when I have a power of a power, such as b to the power of x all to the power of y, what I'm doing here is going to be b to the power of xy, which basically means b to the power of x times y. So let's try a couple examples of these rules. Again, we'll work through all of these together, just because there's not a lot of them, there's a few. So a, 2 to the power of 3 to the power of 2. Well, I see my two exponents are 3 and 2. I only have one base, so I'm going to multiply my exponents together. So 2 to the power of 3 times 2, which is 2 to the power of 6. For b, 5 to the power of 2 to the power of 3 means it's going to be 5 to the power of 2 times 3, 5 to the power of 6. For c, here I have power of a power as well as division. So I again need to assume that I need to simplify the top and the bottom first before I divide. So here I'll have 10 to the power of 2 times 6 because of the power to a power, divided by 10 to the power of 4 times 3, again power of a power, 10 to the power of 12, divided by 10 to the power of 12. Now I can divide, so 12 minus 12, 10 to the power of 0, which is another rule or a special case that equals 1. So a little bit long because we had to do multiple kind of steps or operations here. This doesn't change if we're using letters instead of numbers. It's still considered a base even though we use letters or variables. So r to the power of 5 times, or to the power of 2 becomes r to the power of 5 times 2, r to the power of 10. For b, same thing. S to the power of 4 to the power of 3. This becomes s to the power of 4 times 3, s to the power of 12. And finally for c, p to the power of 3 times p to the power of 2, all to the power of 4. I need to use my BEDMAS or order of operations. I need to use or simplify the brackets first, which is a multiplying of powers, which is different from a power of a power. So in the brackets I have p to the power of 3 plus 2, all to the power of 4. I get p to the power of 5 to the power of 4. Now it's a power of a power, so it's 5 times 4, p to the power of 20. Now again, for some of you that are going through this, you may not need to show every single step. I'm just going through and showing every single step and showing what the actual operation is of how we got our final answer, just in case, or just so that when you're looking back, you understand where these final answers came from. So again, you'll have some practice on these, but again, you're basically, hopefully you understand that there are 3 rules when dealing with powers. When we have a power of a power, we multiply the exponents. When we have a power divided by a power, we subtract the exponents. There is a special case that when anytime you have the exponent of 0, the answer, or it always simplifies to 1. And this only works for when the base is anything but 0. And then finally, when we multiply powers with the same base, we add the exponents. So those are the 3 rules in one special case that you're going to be really focusing on in this course. So please make sure that you are familiar with them and you do understand what those rules are.